Hi everyone, I hope you're enjoying your break. I'm going to be running through online workshop 7 and I hope this is going to help you study. So question 1 is asking, out of these three, which ones does the equilibrium lie towards the right? So basically what it means is compare the left column to the right column and see out of those two, like A or B, which one is going to be the most stable. So if we look at 1I, we can see that they're both in the ketone form, the carbonyl form, while one of these is in the ketone form, and the other one is the tautomer, is the enolate. Now basically what we've been saying is that the ketone form is always going to be the most stable, but there is an exception, and this is the exception, because if you see here, if you put this in the enol form, you're going to be making a conjugated system, which is basically saying that, if you recall from previously, you have a conjugated system like this with the double bonds, you could do the same thing here. So this one, the equilibrium is going to lie towards the right. So true. And remember what we just said previously, up here, the ketone form with this rare exception is going to be the most stable, so this equilibrium is going to lie towards the left. And I think that they just gave this to you as a freebie, because what do you see here? Towards the right, you just made the benzene ring. And we know that benzene is really, 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 really stable. I can't even emphasize how stable that is. So this is going to predominate over the non-benzene form. So the equilibrium is going to lie to the right. So this is 1 and 3. So the answer is D. And let's move on. Okay, so this is basically asking about doing your deuterium replacements that has been pounded into your head since Orgo 1. And what you see here, you have minus OD. So OD, you could think of it as minus OD, very similar to when you see minus OH. They're both really, really strong bases, and they're going to want to pluck off an acidic hydrogen. Now here, where do you see an acidic hydrogen? We know, as our little cheat, instead of having to draw residence structures, we know that the alpha carbon, which is this carbon here, and basically how you identify if something is an alpha carbon is it's the carbon next to the carbon of the carbonyl. So right here we have the carbon of the carbonyl, and that carbon right next to it is the alpha carbon. So we know alpha carbons, hydrogens, are acidic. Now, as a quick glance, I really don't see any other acidic hydrogens here, because if I plucked a hydrogen off from this position, I wouldn't really be able to resonate. So I'm going to have my minus OD come in, and it's going to pluck off. It's going to donate those electrons, and what you're going to form is this. I'm just abbreviating the benzene ring as R. Is this. Forgot my minus sign. And what this is going to do is it's going to go and it's going to attack and you're just going to put a D deuterium in place of the H. Now the question is, as we see here, okay, well right off the bat we could eliminate 3, because we know 3, you could see that it replaced these hydrogens with the deuterium, and that is not an acidic hydrogen. Those were not acidic hydrogens. They weren't on the alpha carbon. They're actually on like the beta carbon or something. Beta carbon. So no, you can't replace those hydrogens. They're not acidic. So then the question is it going to be 1, 2, or an equal amount of 1 and 2? So right now you have made a planar intermediate and you're going into a chiral compound. Would you be able to control the stereochemistry of this? As in, can you say, well, I'm going from planar and I'm going to add the deuterium to the back, or I'm going to add the deuterium to the front? You really can't decide that, so you're going to be getting equal amounts of the both of them. So it's D. Okay, so draw the most stable contributing structure of the intermediate formed in question 2. Oh, darn, why did I erase it? Okay, well, we're just going to draw that again. So we said that the intermediate is going to be this. Now, this isn't really stable because right now you have the negative charge on the carbon, and that is just something that you don't do. Again, it's concepts that you've learned previously in organic chemistry, that you should not put negative charges on carbons or positive charges on carbons. So we're just going to resonate that to get into a more stable form. So this is your answer to 3. We just formed the enolate. Okay. So 4, select the correct statement concerning. All right. So again, let's see how you can get to both product X and product Y. So to get to X, you needed to remove this hydrogen, donate those electrons, and push up. To get to Y, you would take hydrogen from here, donate those electrons, and push up. So now let's go ahead and read the choices that we have. Both X and Y will be formed in equal amounts in any base. Okay, so we can determine that this is not true because depending on the type of base, it's going to favor going one way or going the another. So let's say you were reacting with a big bulky base. If you remember, you had the tert-butyl, so that's a very big bulky base with the negative charge. So tert-butyl is going to have a lot of difficulty getting to areas that have a lot of density in them. So it's going to always want to go towards the least substituted hydrogen. So if you had a tert-butyl, it would go to this hydrogen here. And it will go to the second hydrogen in blue, but a very, very small amount. So A is out of the question. So X is a kinetic enolate and Y is a thermodynamic enolate. So let's just talk really quickly about kinetic and thermodynamic. So kinetic enolate is usually the least substituted, and it's faster formed. It's formed faster. The thermodynamic is more substituted. It goes a little bit slower, but it's the most stable. Okay, so let's see here, which one is the most stable? Y is the most stable because it has a more substituted double bond than X, it would also occur a little bit slower because it's going to be harder to get into that position of the hydrogen that we have drawn in on the other side. So Y is the thermodynamic, and this is saying X is a kinetic and Y is a thermodynamic. Oops. So your answer is B. Okay, this is one of my favorite questions because it's just really, really strange. Okay, so I'm going to run through this really fast. You know, the fetal crafts, alkylation stuff. Hopefully by now it was on your first exam. Now, this combination here is something new. When you see these three, 1, 2, 3, it's called the haloform reaction, and it's really, really interesting, and we're going to run through the mechanism really quickly right now. So we have the Br2 and NaOH. So the NaOH, of course, it's going to be a base, and it's going to want to target acidic hydrogens. And it's going to come in, attack those hydrogens, donate, and push up. Oh, shoot, what am I doing? Okay. Please excuse that big flub. Okay, so for the sake of understanding, I'm going to draw in those hydrogens. And now you form the enolate, and the enolate can react with something, namely the Br2. It's going to push those electrons down, they're going to swing here, they're going to grab the Br, and you're going to get something that looks like this. Now, there's nothing stopping this NaOH to come in again and pluck off this, and then again and pluck off this and replace the both of them with the Br. So you're going to run the haloform reaction, and it's going to remove all of the acidic hydrogens and replace them with the Br2, or I think it just really be any halogen, so X2. I've only seen it with Br, and you're going to get this. And next you're going to react that, I'm sorry, I'm running out of room, with water, or excuse me, not water, it's going to react again with the OH, and that's going to come in, attack the carbon of the carbonyl, swing up, come back down, and kink off this. Now why can this leave? Because right now you just made a CBr3, which is going to be a relatively okay leaving group, very similar to CF3, which is also a relatively good leaving group. Not the best, but it works. And you're going to be left with OH. But now remember, you are still in basic conditions, so you can never really have acidic, can't have alcohols or the alcohol portion of the carbonyl, of the carboxylic acid protonated, because you are in a base. And that is going to come in and it's going to pluck that off, and you're going to be left with this. So after step 1 and step 2, this is your product, and you're just going to protonate it with H3O+. and this is what you get. I'm sorry if it's a little bit mumbo jumbo and I'm like drawing on top of it. I just ran out of room. So 6. So 6 actually was giving me a hard time, and I needed to just stare at it for a couple of minutes and brainstorm. So right now you have, I don't even know what to call this, a butyl lithium. So it's a lithium that has 1, 2, 3, 4 carbons. Lithium. Okay, butyl lithium. And if we look here, this is very, very strangely similar to LDA. Now this is also why it's really important to know the chemical structures of reactants that you have been working with, and not just know their abbreviated forms, because if you're given something like this, you're not going to be able to know, oh, I could relate this to LDA. So what this is going to be doing, it's going to be a strong base, and it's going to come in and it's going to pluck off a hydrogen and give this a negative charge, making your LDA. Okay, so now you have your LDA, and you're going to react it with this. Now you have 2 acidic hydrogens, acidic hydrogen here and acidic hydrogen here. So we're going to call it A and B. Now, how would you know which one to go for? Are you going to go for the kinetic product, or are you going to go for the thermodynamic product? So are you going to try to make the most stable enolate, or what? The thing is, LDA is a big, bulky base. So big, bulky base. I call this a BBB. And it's, again, very similar to the tert-butyl. It's going to have a difficult time getting into tight areas and plucking off a hydrogen. So it's going to go for the less substituted. It's going to come in, it's going to attack, it's going to pluck off, it's going to donate the electrons and push up, and you're going to get this. Now, if you can see, there's also an Li here. So instead of drawing it like this, you can draw it in coordination with the Li, because the Li is just going to be floating around after it plucked off the hydrogen. Look at us, we're just like speeding through this whole workshop. No? Okay, so 7, predict and draw the major product of the following reaction. Interesting. Okay, so we can see that our final product has 3 oxygens in it. And over here we have the enolate that we can attack this compound. So we're going to go and swing down, and it's going to attack this compound somehow. Now, the question is, would it attack here, or would it attack here? Well, they're kind of making it easy for you because they're giving you the chemical formula, and they're saying that your final product is going to have 3 oxygens in it. Now, if it attacks, let's label this one A, label this one B. If you follow arrow B and it attacks, it's going to swing these electrons up, come back down, and it's going to kick this off. And alas, you're not going to have 3 oxygens in it. So let's go with A. Excuse me, don't know my alphabet. So it's going to attack this carbon position, and it's going to kick off the Br, and you're going to be left with the Li positive with this. Now the Li is going to donate its electrons and leave, because you don't want a carbon with the positive charge, an oxygen with the positive charge, excuse me. and this is going to be your final product, and the Li that left is going to be floating around in the solution in association with the Br. Okay, so again, I'm going to run through this really fast because I hope that you guys have gotten this concept into your head from the previous problems. You have LDI. LDI again is a big bulky base. And it's going to go for acidic hydrogens. You have acidic hydrogen here and you have acidic hydrogen here. Let's label them A and B. Now we know that big bulky bases are going to go for the least substituted. So B is the least substituted. It's going to have the least amount of steric hindrance, and it's going to come, attack, donate the electrons, push up, and it's going to form that enolate. So now you have formed that enolate, and this enolate is going to be able to attack this second thing. It's going to attack that carbon. It's going to push off the leaving group, which is the I. Remember, leaving groups are like your halogens. You have the I, Cl, Br, those kind of things. And you're going to get not that. You're not going to get that double bond there because your double bond just attacked and formed this new bond here. So that's your final product for 8. So let's go on to 9. Okay, so 9 is something called the Stork-enamine reaction, and the mechanism of it isn't really fun, but basically I'll go through it for you. You're going to attack. Okay, you cannot see that color really well. And you're going to protonate the oxygen, and you're going to have this in here. Its lone pairs are going to come and attack that center carbon of the carbonyl. It's going to push those electrons up. Now, if you're familiar with any of the other enol or the other carbonyl reactions, this is just literally the same reaction that's performed over and over and over again. And you're going to have a proton transfer here. Okay, now this is going to come, it's going to swing these electrons down, and it's going to kick off that water. And you're going to be stuck. Oh, excuse me. I had that connected to the wrong place. Okay. And you're going to have something that looks like this. Okay, so draw this mechanism down. I am going to erase that and just redraw that intermediate. Previously, I forgot the methyl group over here, but it's not that big of a deal. So you have this. Now, you have the possibility of taking hydrogens from here or here to form like an enolate-esque compound. And if you remove it here, you're going to donate those electrons. You remove here, you're going to donate those electrons, and you're going to want to make the most stable enolate-esque compound to just, and I'm calling it an enolate-esque compound because it's going to be the same type of concepts behind it, you're going to want to form the most stable enolate, unless you're working with the big bulky bases. And the most stable enolate is going to be the one that has the double bond that's the most substituted. So we're going to go for this hydrogen because it's going to make the most substituted double bonds as we can see. Didn't mean to do that, but it's okay. Okay, so you're going to make this. So that was all just for the first step. And now we have something that looks really, really similar to all the enolate reactions that we have been working with, where the electrons swing down and it pushes that double bond off to attack something. You can do the same thing here, where the lone pairs come down and it pushes this double bond to come in and attack this carbon. Attack the carbon, not the Br. You don't attack leaving groups. And the Br leaves, and you'll get stuck with this. And when you add water, you're going to basically remove that amine group, cyclic amine, and you're going to replace it back with the carbonyl. So this is E. Ooh, I love these. Alrighty, so what you're going to be doing is you want to synthesize that. I find these questions a little bit difficult because they're giving you a set reagent, so you're really limited in your creativity on how to approach these problems. Okay. So I think I'm gonna start backwards and forwards at the same time and try to just meet them up in the middle. So starting from going backwards, I see that I have a Br in my final compound, and I'm searching through these and trying to find a reaction that would add a Br on. And it's not going to be this or this, because in these situations the Br is going to be the leaving group, as in you attack this carbon and the Br leaves. But here, I could add the Br. And the way that works is, again, you're going to have that enolate reaction. So working backwards, I'm going to put I. And running that forward, it would look similar to having this. It's a double bond, and it's going to attack the Br to get this. Now that leaves me to the issue of I am going to need to somehow deprotonate this and make the enolate form. So then I'm going to look for a base. Well, I can't really go anywhere from backwards from here either, because I totally miss this. Here we have 4 carbons in our backbone. And here we have 5 carbons in the backbone. So there is an extra step that we should follow. And I think to add on a carbon here, and what I'm going to do is I shall attack it, have this, attack this, and then it's going to go E. So it's going to be IE. But it's a little hard to visualize in retrosynthesis, so I'm going to show you going forward. So going forward, I can't really do anything with this because it's protected. So I'm going to add F, the acid, and it's going to remove that acetal protecting group on my carbonyl. and I'm going to want to add something here. I'm going to want to add the carbons on it. I'm going to want to have E. Now I have this with F, and then I'm going to put my base on, and now I have the choice. Do I use A as my base, or do I use G as my base? So the thing is, I want to make the least stable enolates. I want to remove a hydrogen from this position here rather than this position. If I use NaOH, it's going to go for the most substituted because it's small enough and it's going to be able to form that most stable enolate. On the other hand, if I use LDA, it's going to be really, really selective, and it's going to go for the least substituted. So it will go for the hydrogen that I want. I'm going to have this. And then I'm going to react that with E. So what I just did was I made this backbone, which I could then follow up with I. So the final is going to be F, G, E, I. I know that was a little bit confusing. I hope this helped everyone, and if you have any questions, just ask in the comments below. Feel free to Facebook message me or post something in the group. I monitor regularly. Good luck studying and enjoy the rest of your break.